Benchmark solution 4.5, a 480 volt, 200 kVA, 0.8 power factor lagging, 60 Hz, 2-pole Y-connected synchronous generator has a synchronous reactance of 0.25 ohms and an armature resistance of 0.03 ohms. At 60 Hz, its friction and windage losses are 6 kilowatts and its core losses are 4 kilowatts. What's the excitation voltage of this machine at rated conditions? How much power and torque must the generator's prime mover be capable of supplying to meet the conditions in Part A? And C, what is the counter torque produced by the armature reaction? So, some labeling problems there. Givens in this problem is that the terminal voltage is 480 over root 3. The three-phase apparent power magnitude is 200 kVA. The rated power factor is 0.8 lagging. The electrical frequency equals 60 Hertz. The number of poles is 2. The armature resistance is 0.25 ohms. Armature reactance is 0.25 ohms. The armature resistance is 0.03 ohms. We know that it's friction and windage losses, so that's power, friction, windage is 6 kW. Core losses equals 4 kilowatts. We're asked to find EF at rated conditions. The input power, that's how much power and torque must the generator prime mover be supplied. So we call that PN, that's the input power from the prime mover, and the torque applied by the prime mover. And then the counter torque is the torque caused by the armature reaction. We call that torque induced. So hopefully Part A is old hat at this point. We've got a generator model that looks like this. And so if we want to solve for EF, we need to know what the load current is right there. So we just have EF is equal to the terminal voltage plus IA times RA plus JXS. That's the circuit model for that. We need to determine what the magnitude of IA is. That's just the per phase power divided by the terminal voltage. So that's 200 e to the third over 3 to get it on a per phase basis, divided by 480 over root 3, right? Those numbers came from here and here. So that gives me a current amplitude of 240.563 amps RMS. And then I can determine the power factor of that by taking the inverse cosine, the angle of that current by taking the inverse cosine of the power factor. That means at rated conditions, IA is equal to 240.563 at an angle of negative 36.87, the negative because that's a lagging value. So that gives us that number. We can now sub that into this equation to get the excitation voltage. EF is equal to 480 over root 3 at angle 0 because VT is taken as the reference. Now I just sub in IA. And then I can put in the synchronous impedance, which was 0.3 plus J 0.25. get an excitation voltage of 321.977 at an angle of 7.82 degrees volts. So that's solution for part A. Part B asks us to determine the input power and the torque applied to deliver this amount of output power. So to do that, we have to consider generator losses. So we've got basically this model here. We've got the input power. There are a couple loss mechanisms that we have to account for. That's supposed to be an arrow. That's a terrible arrow. The first is that we've got some sort of three-phase loss associated with the friction and winding of the generators. Then we've got some three-phase loss associated with the core. And then we've got some three-phase loss associated with stray losses. And that input power then gets converted over into EF. So we call that the P converted. So that's how much of this input power actually made it into producing an electromagnetic field that resulted in EF. And then there's one more loss mechanism. And that loss mechanism is the copper loss. That's the heat due to this here, PCU, sometimes called Pi squared R, since the copper loss is due to resistive heating. And then we get P out. So these values were given to you in the problem statement as, well, let's look, 6 kilowatts and 4 kilowatts. We're going to assume that's 0 kilowatts since it wasn't given in the problem statement. If we want to know Pn, we can just add 6 kilowatts, 4 kilowatts, 0 kilowatts, Pi squared R, and P out. But we need to have values for these two to be able to do that. So P out on a three-phase basis is going to be equal to 3 times the magnitude of the line current times the magnitude of the terminal voltage times the power factor cosine of phi. So that's equal to 3 times the current, which was 240.563, times the terminal voltage, which was 480 over root 3. Cosine of phi was just the power factor of 0.8, so that's 160 kW is P out. I could have also just taken the three-phase power rating and multiplied it by the power factor. So that's 200 kVA times 0.8, it's 160 kilowatts. So a couple methods you can do that. So that is how much power this thing is delivering at rated conditions. It's 160 kilowatts. Now we need to determine the copper loss. We already discussed that that's due to I squared RA heating. So that's 240.563 squared times 0.03 ohms, and that gives me 5,208.35 watts. So the input power is, just sum all those together, 160 e to the third plus 5,208.35 plus 0 plus 4 e to the third plus 6 e to the third. So that gives me an input power of 175,208 watts input to get 160 kilowatts output. And then it asked me to determine how much torque needs to be applied by the prime mover to deliver this much input mechanical power. And we know that the relationship between torque and power is just we take the torque and we multiply it by the mechanical rate of rotation of the prime mover. So that's at the input, that's P in power from the prime mover has got to be the torque applied by the prime mover times whatever speed the prime mover is rotating at in radians per second. So we don't know this number yet. We weren't given that information, so we have to determine what the angular rate of rotation of the prime mover is, and hopefully it makes sense that we just get that from electrical frequency, since we know that there's a fixed relationship between mechanical rate of rotation and electrical frequency. And so that is, excuse me, mathematically, the angular rate of mechanical rotation is the RPM of mechanical rotation times pi over 30, and that's just converting from RPM over to radians per second. So we've got that, but next we need to determine Nm, and that is that we can just plug in, that is, we take 120 times the electrical frequency divided by the number of poles. That gives us Nm, mechanical rate of rotation. And then we just multiply that by pi over 30. That gives us the angular rate of rotation radians per second. So for this problem, we get 120 times 60 hertz. It was a 2-pole generator. And then we have our conversion from RPM to radians per second times pi over 30. And that gives us about 377 radians per second. And so I can determine the applied torque by the prime mover by dividing the input power by the rate of angular rotation. And so that's 175,208 watts divided by 377 radians per second. And that gives me 464.76 Newton meters of applied torque by the prime mover in this situation. So that was Pn and applied torque, which were part B here, and then part C asked us, well, what's the armature reaction torque applied? So the same relationship applies. We're just measuring at a different point in the system. Instead of measuring it here, which is the input, we want to know the armature reaction, which is this guy. So this amount of power P converted is got to be P out minus this loss mechanism. So P converted equals P out minus the copper loss. And P converted equals the torque induced by the armature reaction times the mechanical rate of rotation, and P converted is equal to the output power minus the copper loss. So that's equal to 160 kilowatts minus 5,208.35 watts is 154,792 watts for the converted power. That's how much of the power actually made it into EF, the excitation field. And so we can calculate the induced torque by the armature reaction by just taking 154,792 divided by the mechanical rate of rotation of the armature field, which is the same as the mechanical rate of rotation of the prime mover. They're in synchronism, so they're locked. So I need to divide by 377. So I do that, and I get 410.59 Newton meters of torque induced by the armature reaction.